So hi everyone, hear me? Is it working? Okay, so thanks. So welcome. So I'm giving the lecture today because Professor Leskovic is traveling. I'm a postdoc in the group, and I'm going to talk about influence maximization. So this is one of those cool topics which you can see concretely in your life. So it's exciting to hear more about it today. And so let's get started on that, and feel free to ask me questions whenever you have one. Okay, so marketing research showed that we are more influenced by our friends and family and people whom we know compared to random people. For example, the researchers have shown that 68% of people consult their friends, but only 50% go and check like reviews online about a product when they want to purchase something. And the reason is that we can trust our friends and family more than random people and random reviews. So it's really important to kind of analyze this process when we want to maximize like the influence or adoption of behavior throughout our network. So if we have like a network, underlying network, and we have like a model of how the influence spreads throughout the network, we can identify the influential people. For example, we can, if we want to like maximize the adoption of a behavior or a product, we can try to find these influential people. We can try to convince them to adopt this product and then advertise it basically with the word of mouth throughout the network. For example, in Instagram, influential people are paid to kind of talk about a product, or we can offer them discounts, or we can find them free samples, and then the product will be adopted, or the behavior will be spread throughout the network. So these customers can like advertise, they can endorse the product, and kind of other people in the network will see and adopt the behavior. So for example, and then we don't need to do any other marketing, kind of, we don't need to do anything else, like marketing efforts or something, and then this behavior or product will be adopted by a large fraction of people in the network. So it's really important to find those initial seed of the most influential people for this. One example here is that, for example, Hotmail, when it was new, so in the bottom of every email, they were written that this email is sent through Hotmail, and if you want like a free account, Hotmail account, you can come and sign up and we will give you a free email. Or for example, today's in LinkedIn, you can see that they ask to see your friends, and they encourage you to invite them to join LinkedIn. The same you see in Facebook. So it's something that is really used nowadays and is really effective. So here is like a Wikipedia article about the Kate Middleton effect. This is, for example, one of the recent examples of this influence like spread through the network. So the story is that whatever, for example, she does, like when she wears new clothes, a lot of people would be affected, and they go and buy the same product. And it's shown that she kind of contributed more than 1 billion pounds to the United Kingdom industry. So for example, when she buys and like wears one of these clothes, those companies run out of stock. You need to go to the waiting list to get to buy the product, and so. And kind of today we want to see how you can use kind of what is the effective strategy to find people like Kate Middleton if you want to maximize the spread of your product or information or anything throughout the network. So it's true that influential people often have many friends. Like, for example, Kate Middleton has a high degree in the network. But it's not the case that if you can just identify the high degree people, then you can maximize the spread of the influence throughout the network.
What network is this?
This is just an example. I'm not sure if this is like, yeah. So it's not correct that only high-degree people are the best options for maximizing the spread of some piece of information in the network. And the reason is that a lot of times, these high-degree people, the friends of these high-degree people or the neighbors have overlaps. So they have a lot of common friends. So it's not optimal if you just go and take those high-degree people who are very close in the network to each other. So we really want to maximize the spread of influence throughout the network, in all parts of the network. So it's really not easy to find people like Kate Middleton that can maximize the influence in your network for you. So what can we do? So this is kind of the problem definition of influence maximization. Given that we have this directed graph, we want to find the small subset of K seeds. Yes?
Sorry, I just wanted to ask, so does this intuition about it being sort of more complicated than we think extend, even if you use something like PageRank? Like, it's also not sufficient just to take the kind of most central.
Yes, exactly. Yes, that's true. So here, the problem is that we want to find this small set of K seeds, or K most influential people, who can maximize the number of people that are influenced by these small seeds. And possibly in many steps, we don't want to only look at the immediate neighbor of this small seed set. So we have, like, to study this problem, we need to first define like a model for this spread of influence throughout the network. So here we discussed two classical models for propagation. The first one is linear threshold model, and the second one is independent cascade model. Let's start with linear threshold model. So here, every node has a threshold, like, for example, uniformly at random between 0 and 1. What does this mean? It means that I need my friends to like influence me more than this threshold so that I'm convinced to adopt the behavior. So if I have, like, let's assume B is the weight that each of my neighbor has on me. And this kind of shows the amount of influence that each of my friends has on me, or kind of the degree of trust, like how much I trust each of my friends. And if the sum of these influences or the sum of this trust is above this threshold that I have, then I'm convinced and I adopt the behavior, or I sell or I buy the product. So this is a linear threshold model, and the reason we called it linear threshold is that we take a sum over these influences that I get from my neighbors, and the threshold is that every person has a threshold to be convinced. So here is an example. So let's assume this is the network, and these are the thresholds for different people, the blue bars. So if this node V, is now getting active, it can influence like by 0.2 U and by 0.5 W. And now, so this is like this is the threshold for W, for example, and this is the influence of V on W. And now you can see that this influence that W gets from V is greater than its threshold. So this one is going to adopt the behavior, but this one, because the influence is less than its threshold, it's not going to adopt the behavior. So in the next step, W gets active, and then W influences each of its neighbors by the weight of every edge. And for example, here, this node X is only influenced by W, but this node U is influenced by both V and W. So the influence that U has from its neighbors is a sum of 0.3 and 0.2. And here, because this influence is now greater than its threshold, it is going to adopt the behavior and become active. So we keep continue like doing this process until there is nobody else that is kind of become activated. So this is kind of the linear threshold model. So the next model is like independent cascade model. And this model is the one that we are going to talk about in the rest of this lecture. So you might want to pay a bit more attention to it. So this one is a probabilistic model. So linear threshold was deterministic. So the weight of every edge was fixed. So independent cascade is a probabilistic model. So we have this graph G with a set of nodes V and a set of edges E. And we kind of activate a small set S of nodes in the network. And now there is a probability assigned to every edge in the network. Like P of VW is like the probability that node V can activate node W. And every node, after it becomes activated, has only one chance to activate its friends with the corresponding probabilities of the edges. So it doesn't matter, like, among my friends, who is trying to activate me first. Like, if I'm activated, then I stay active. And it really doesn't matter how many people can activate me. So nobody is counting me twice. So the number of activated people is matters kind of. And yeah, and everybody has one chance. And we go over time. Like, we go step by step, and at every step, everybody who is active and didn't use his chance before can activate new nodes. So here is an example. So in this graph, kind of A is the active node that we have. So among its neighbors, so among the edges that it has, so he can try to activate any of his neighbors by these probabilities, and he only has one chance. So he flips the coins, he draws random numbers, and for example, this edge, like between A and E, it selects this edge and E infects E. And now E becomes active again. And now at step 2, so A has already tried, now E is going to try to activate its neighbors with the corresponding edge probabilities. The outlinks is between A to G and to F. So with these probabilities, he tries to activate its neighbors, and he can activate both, let's say. So if we continue this process, this information or behavior will spread throughout the network. And kind of the goal is, who are the set of most influential nodes that we need to activate in the beginning to get the largest adoption of a behavior. Okay, so this is a problem definition, most influential set. We have a fixed size K. This is our budget. This is the number of people we can convince or we can pay. And we want to find the best subset of size K people in the network. So for example, here we start from D. So at step by step, at every time, this information can spread. And kind of this is the influence set of D, meaning that after this process is finished, like after a couple of time steps, here after 3 time steps, so these green nodes are the influence set of D, meaning that these are activated by D. Now if we look at A, so A, for example, after 3 time steps can activate this set of nodes. So if we start with an active set of A and D, then these are the number of people that are adopting the behavior. For example, we have 8 people who are active here, and we are not going to count G twice because we only care about how many people will adopt the behavior, not how many times. And now the goal is that we can find an initial seed set that maximize the union of cardinality of these influence sets for the initial active set. So this union, we show it by F of S. S is the initial set of people that we can activate. So something, if you have noticed here, is that I said this is like a probabilistic model. We don't know if I try to activate you, either if I will be successful or not. So because this is a probabilistic and randomized model, we need to take expectations. We need to think about expectations. Like in expectation, how many people I can activate after t time steps, right? So the definition is clear, right? So this f of s is kind of the expectation. Like if you think of fi as one possible outcome of this probabilistic process, like I try to activate you and then you try to activate your friend and so on, this is just one outcome. Next time, if I try to activate you, you may not become activated at all. So different tries, because it's a probabilistic behavior, each of those tries are I. And then I want to take an expectation over all these possibilities. So this is what I care about, and this expectation is the one that I want to maximize. Any question about this? Okay, great. So, for example, and like this is kind of an intuition that what is the set that we want to find. So imagine here now that, for example, this is the part of the network that is being activated by A. Like if I pay A, like something to advertise for me, he can influence these many people in the network. This is the set that is getting activated by D, and these two sets are the ones that B can activate or C can activate, right? And now, what is a good strategy? Like if we want to go with 2 people, if we have the budget to pay 2 people and activate them, who should we select? So here you see that if I choose A and B, so their influence set overlaps a lot. And I don't care how many times I can activate people, I just want to activate people. So the union of these 2 sets wouldn't be large, although each of these sets are large. But now if I try to activate A and C, so the union of these 2 would be larger than union of A and B. And it's even better if I try to activate A and D, because this union is even larger, right? So this is kind of what we want to find. And so now we want to see how hard is finding this initial set of people that can maximize the union of influence sets. So how computationally hard is this problem? So the problem, again, is that, so F is the expected number of people who are activated by initial active set S. And we want to maximize this function, starting from initial seeds S. So this problem is not easy. This is like an NP-complete problem. So intuitively, this means that you need to go and enumerate all the subsets of size k in your network and see each of them has a higher influence in the network, expected influence in the network, right? So that's the definition, kind of an NP-complete problem. Why this is an NP-complete problem? There are 2 hidden slides here. You can read more about NP-hard and NP-complete problems. But basically, we can show that we can reduce this problem to a set cover problem, and set cover problem is NP-complete. So this problem is also NP-complete. So it's not easy to find the best subset of size k that maximizes this influence for us. It's NP-complete. So what can we do? So the bad news, you saw already, it's not easy to find the best set in the network. The good news is that we can find the approximate solution. What does that mean? It means that, so although I cannot find the best subset of size k in my network, I can find a subset that kind of guarantees a worst case approximation for me, meaning that, so the approximate solution that I find, if opt is the best set of size k that gives me the highest or largest influence in the network, the subset S, I can find a subset S that is guaranteed to be 63% of this influence, that is guaranteed to give me 63% of the influence in the network. And 63% may not look very good to you, but in practice it works better than 63. Like this is the minimum, this is the worst case. So now how can we find such a solution? How can we find such an approximate solution? So what we will see is that we can greedily select this initial set of k nodes and get the approximation guarantee. And I'm going to kind of walk you through these steps. Why do we get that approximation guarantee, and how does greedy work? So the input to this greedy algorithm is like for each node, you saw that like with that probabilistic independent cascade models, there will be a set of nodes that are being activated in expectation. So that is the input to my problem. So I know for every node how many people in expectation are going to become active. And at every step, so greedy algorithm works in rounds. At every round, it's going to select the person who make this union the largest, union of activated people, the largest. So here is an example. So we start with an empty set. In the beginning, we haven't selected anybody, and we want to select k people. So in step 1, we select the, let's say, highest degree person, right? Because that is the one most probably, I mean, it depends also on the probabilities on the edges, but let's assume that that person can maximize the influence in the network for us. We are going to select that person. We select that person, and this is actually an example. Let's assume these are kind of the influence, the size of the influence set for different nodes in the graph. So we are going to select greedily the maximum one, the one who maximizes the influence for us. So we are going to select D. And now in the second step, we see that condition on D, like D is already selected, we are not going to throw it out from the set. Who is the next person that we can add to D to maximize the cardinality of people who will be influenced in expectation? So we update all of our benefits. So now, given that we have selected D, A, B, C, E will be like different, activate different number of people in expectation. So among these new like benefits, we are going to greedily select the best one, and we add it to D. And we keep continue doing this process until we get k element. Yes?
Can you go back to the previous slide real quick? So you're saying for each node U, you have the set of that it can influence, right? Is this like a pre-processing step where you?
We are going to talk about it, yes.
Okay.
Yes. Like assuming you have that, you can run greedy and find your subset. But how to find that, we are going to talk about. Okay, so the greedy is clear, right? So intuitively, it's like if I select a high degree person, I shouldn't select one of his friends most probably, because those unions will overlap. But if I select a, let's say, high degree person from another part of the network, because those friends do not overlap, it gives me the higher number of influence people, right? Okay. So now, how does greedy gives us an approximation guarantee? So 1 minus 1 over E is that 63% that you saw in that previous slide. So if our function has two properties, this simple greedy algorithm gives us 60% approximation guarantee. What are those properties? The first one is that if is monotone. What does that mean? Adding an element to your subset cannot decrease the number of influence people, right? So in the worst case, the number doesn't change, but it wouldn't decrease. So this is like a monotone. By increasing the number of people in the subset, your function would either increase or doesn't change. The second property is that F is submodular. So what does submodularity mean? So it means that, let's say I have two sets, S and T. And let's say S is a subset of T, like S is a smaller. If I take one person, this person U is fixed. If I add it to the smaller subset, he benefits me more than if I add U to the larger subset. So this is the diminishing returns property. So as an example, imagine that, so I am the only activated person. I am S. Second case is that I am activated, and for example, he is activated as well. And now, if we take another person, if we both try to activate you, he can help more than if I, like, let's say, add him to like 3 of us. Like, the difference would be more if the subset is smaller, right? Was it a bad example? So if I have a smaller number of people in my subset, and if I add somebody to this smaller subset, the number of influenced people will increase more than if I have a larger subset and I add the same person, right? This is diminishing returns. The more I have, the less I gain.
Because it's like proportional to the size of some
Because of the overlaps, right? Because the more people that I have, there is a higher chance that if I select a new person to add, his friends overlap with the people who are already influenced. So this is kind of a demonstration of submodularity. So this is kind of the cardinality of sets. S is a smaller subset. If I add U, the increase would be more than if I add U to T because of those overlaps. Okay, so now we kind of have to prove that first, our influence function is submodular, and second, greedy gives us an approximation guarantee. Yes?
I hope this isn't too much of a tangent, but like, I'm just curious, is it useful to just, in general, calculate the influence of any individual node, have that as like a feature for other algorithms we've talked about before? Because you're talking about finding like a subset, but each individual node has its own influence anyways, so that's...
We have to calculate that.
Yeah, so I mean, just that right there is already like a powerful feature probably for other things. I'm just curious if that's like used.
Like?
Well, like, I don't know, we have these features we developed, like degree and centrality and all these, so if you just calculated that number.
Yes, so that's a very good feature, actually. Yeah. Like, that's a very nice feature. The only problem is that it's expensive to compute compared to degree, let's say. So we are going to talk a little bit about this complexity like later in the lecture and how to estimate that. But yes, that is I would say that is a really nice feature if you want to use usually. Okay, so we have 2 steps in our proofs. So we are going to mostly talk about the first one. The second one, you are going to see the proof in handouts. I can give you the intuition why that works. But you can, like, for those of you who are excited to see a couple of more equations, there is this nice handout uploaded on the website, so you can go check that out. So, okay, so we talked about what are submodular functions. Diminishing returns property, you add something to the smaller set, the benefit is more. So there are a couple of basic facts. So the positive, let's assume these are some positive scalars. The positive combination of a couple of submodular functions is still submodular. For example, if you linearly sum some concave functions, the resulting function would be still concave. So for in our case, and the fact too is that, so this is our influence function that we have. So if we have k elements in our set S, and this is the influence set for each of those people, we are interested to find the cardinality, the union of the people who are activated, and we want to show that this function is submodular. And currently, I'm not talking about the probabilities or anything like that. We just assume that we know what is the cardinality of X, right? So this is kind of an example of a submodular function again. Let's assume this is T, this is S, this is the set S, like this is these three people are in S, and this is the area that these are covering. And I want to add U to my set. And I'm interested in the whole area that these elements together can cover. So the benefit of U, condition on S, is this much, right? Minus this part. So this is how much I gain. This is the marginal gain. And now imagine I have a superset of S, which is T. Like I have everything in S plus 2 more elements. Now if I try to add U to T, the benefit that I get in terms of the area that I'm covering is less. So this is kind of the same concept that we talked about. This is kind of, yeah, submodularity. And we want to show that the union of the number of people who are influenced in our influence maximization problem has this property. Okay. So here we want to kind of show that why our influence maximization problem is submodular. So I mentioned this briefly. We can reduce this problem to a set cover problem, and kind of the example that you just saw, you can also think of it as a set cover problem. So, and as I already gave you as an example, the more people that I have, there is a higher chance that if I add somebody, the influenced people would have already been influenced, so we get less benefit. And now let's talk about the probabilities that I have in my independent cascade model. Because we talked about this is a probabilistic model, and right now whatever I told you was assuming we have these deterministic edges basically, right? Now let's see how we can deal with probabilities. So we are going to use this principle of deferred decision, meaning that in the original independent cascade model, I try with some probability to, for example, influence you, and the next step, you try with some probability to influence the other person. But the way we can think about it and simulate the same thing is that all the edges in the network has some probability. I threw a random number for each edge in the network, and I can see which edge would be active, which edge wouldn't be active, right? So I can do all that in one step. I threw those random numbers for all the edges, and I kind of reduce this probabilistic process to a deterministic one at one step for one trial. So I'm going to talk about this more now, so don't worry. So each of these tries, so okay, we can go to the next slide, or this one. So I talked about the expectation, right? And I said that the expectation is over the number of people that I can, for example, activate through this independent cascade process, right? And now we want to kind of break this expectation to different trials, like we are talking about each fi in the sum in our expectation, how we can calculate that. So this is kind of your question, how can we calculate x for somebody, the set x for somebody? So we are going to how do you calculate expectation? You try something a lot of times, you take the average, right? We are doing the same. We are going to do the same. This parallel possible words is that each of those FIs, each of the tries would be one possible word. And we are going to, in parallel, build a lot of instances from our probabilistic network. Why I'm saying probabilistic network? Because each edge has a probability, right? So each time I'm going to try a couple of times. So here is an example. I draw one random number for every edge. If the random number is less than p of that edge, probability of that edge, I assume that that edge is live. So I keep it in the network. Otherwise, I drop it from the network, in one trial. So one trial for all the edges in the network. So that probabilistic network that I have there, this will be reduced to this one, let's say, after I throw those random numbers and I drop some of the edges. So I kind of convert my probabilistic network to a deterministic one. And in this deterministic network, as we saw before, it's easy to see how many people A and D can activate. Now there is no probability in the network. We are just going to see how many people they can reach. Right? So A can reach all of these people, cannot reach B because there is no edge. D can reach E and H, but not I. Right? This is easy, just BFS. So, and this in trial I, you see that, for example, A could activate, like he would be active, and F and C and G would also be active. Similarly for B and C and D, right? So this is like X for each of these nodes in trial I. And now we have to take the average over all I's. Okay, so for the ith possible word, as we said, for example, if S is A and B, now we have all these people, like the union of these two green sets. We take a union of those, and if we activate first A and D, in the end we are going to get 5 people activated. On the other hand, if we are going to select A and D, we will get 7 people activated, like the union of these two sets. So in trial I, this is happening in I. We have to repeat that process a lot of times and take the average over these numbers, right? And then we can select kind of a good subset. So here you can see the examples. So again, for trial I, I'm going to find, for example, in the first trial, so 3 people are activated by A, including A. In the second trial, like 4 people would be activated, and in the last one, only 1. So in expectation, A can activate like the average of these numbers. This would be the benefit of A. This would be the cardinality, the influence of A in expectation. And we are interested to find this small subset that in expectation has the largest influence. And as we talked about, this is submodular. Our F is like an expectation over Fi's, an average of Fi's. And this S is all the people that we have selected. We want to select a subset that maximize this expected, like this Fs, expectation of Fi's. We want to maximize this, and we showed that this is submodular because this is a linear combination of all the Fi's. Any question from this? Everybody are following? Okay. So the recap is that we are simulating parallel words. Yes.
We use these examples to show that it was submodular. Could you just walk us briefly through how these examples show that it's submodular?
Yes. So I can show you here. So if Fi is submodular, then the sum of Fi's are submodular, because this is a linear positive combination of all the Fi's. And the question is why Fi is submodular, basically. So an Fi is the case when in trial I, we flip all the coins for all the edges, or we throw those random numbers, and we kind of convert our probabilistic network to a deterministic one. In that deterministic network, if I have a larger active set, and if I add somebody, the benefit in terms of the number of newly influenced people is less than the benefit if I have a larger active subset.
Because we're measuring it as a percentage of the previous, I thought f of s is just a global, just total size.
Yes.
So each additional person added would be 1, no matter the size of the network.
No. So if we have a fixed network, there is no probability. I already through all those random numbers, the network is fixed. Then the assumption is that I'm going to activate all the people I can reach, not only myself. So there is a number of people that I can activate, and this would be x of me, right? And if I add another person to me, like as an activated person, then he can also activate a lot of people. And then the union of these two sets would be f of s, fi of s, right? And the thing is, if I already have 100 people who are activated, there are a lot of people who are influenced. Now, if I add the one new person to this 100 people, because he, with a higher chance, has a lot of overlaps with this big subset, he can help me less than if I have only one person and I'm activating 5 people, right? That is submodularity. So each fi is submodular and the sum is submodular, right? Yeah.
And so it depends on a relevantly overlapping graph. And so if you have a very large graph or a graph in which the potential second activated node does not interact with the first, then it's not necessarily submodular.
It is, because he should help, like the help that he can do, if there is no overlap, there is just a plus. Like he can never help more if I have more people selected. Like it's less than or equal, right? Yeah. Okay, so yeah. So now this expectation, we can just calculate the average for different subsets, like for first trial, second trial, third trial, and so on. We can take the average, and this f is submodular, so we can use greedy algorithm to maximize the submodular function. If we select k people with this greedy algorithm, we are guaranteed, because this is monotone and submodular, this subset influences at least 63% of the people that the optimal subset can influence. Okay, so now this is what you are going to see more in the handout, but kind of 1 minus over e is 63%. And the greedy, we already talked, we start with an empty subset, and then we try to add elements one by one until we get k elements. And because we have a monotone submodular function, we are guaranteed to get 63% of the optimum. And so, yes?
Some other randomized algorithms have the property where if you have some kind of non-zero constant of success, you can kind of repeat the randomized algorithm over and over and kind of arbitrarily make it as accurate as you want. Does this algorithm have that property? Like, can we run this multiple times and take the maximum and have some sort of exponentially decaying degree that we're close?
So the point is greedy is deterministic. So if you go for a large I, you always should converge to the same solution. Yeah. Yeah, there are other techniques you can kind of, if you cannot run greedy, if you cannot afford, because at every iteration you have to check everybody, how you can use deterministic and probabilistic processes to make it accurate. But for greedy itself, it's deterministic. Okay, so, and this bound, this 63% is data independent, meaning that this is the worst case for all the networks that you can have. So usually, as I said, you get something much better than this. If you can calculate the optimal solution, you will see. But no matter what is the graph, we know this is the minimum that we get from greedy. So we are kind of happy with this. So now the problem is this is kind of expensive. Like calculating f is like you need to calculate like exact, like a very good precise expectation. You have to simulate a lot of parallel words. You have to go with a large I so that you get a good expectation. And if you go with enough number of parallel words, you are guaranteed to get plus minus 1 plus minus epsilon approximation to fs. So this epsilon is because of those expectations that we take like as a sum or average of different number of trials. This is coming from there. So the original greedy gives us 1 minus 1 over e. Because we are approximating or estimating the expectation, we will get this epsilon extra here in our expectation, like 63% minus epsilon. And epsilon depends on how many trials you actually do in practice. Okay. So we already talked about, like, just as a reminder, we have this, we want to find a subset that gives us largest expected influence in the network. And we want to find this set of S at most k nodes in the network who maximizes this expected influence for us. And we have this network that every people can activate their neighbors with a certain probability, like this is a probability between node U and V. And we are going to like generate like big I times like parallel words. Like each time we take our network, we throw those random numbers, we keep some edges, we drop the rest of the edges. We try to see what is the subset of size k people that can maximize the influence for us. Or we basically calculate for each node how many people it can influence, and then we take the average of influence for every people for different parallel words that we have. And for example, for A and D, in the first word, it's like 3 plus 3 nodes are becoming activated. In the second one, like 4 nodes we get here activated. The last one, we get 3 nodes activated. So in expectation, A and D can activate like 3.5 kind of people for us. Okay, so any question from this? Okay, so now this is great. We have an algorithm. It can give us an approximation guarantee. The only problem is that it's slow. Like imagine you have a very large graph. You want to try 10,000 times, simulate these parallel words, convert your network to a deterministic one, and then do BFS to calculate the influence of every person. So this is slow. So the complexity of this process is like k, the number of people we want to select, times n. This is the complexity of greedy itself, because we have to make k passes over all the people and select the best one greedily at each iteration. So the complexity of greedy is k times n. N is the number of nodes. R is the number of parallel words that we simulate. And M is the number of edges in the network. Because for each of those parallel words, you have to do a BFS and see how many people every single node can infect, right? So once again, this is only for greedy. And every time that greedy for each of these k times n, like I make k passes through all the nodes in my network, I have n nodes. Each single time that I want to see how influential is a single node, I have to simulate R parallel words. In each of them, I have to do BFS. Right? So this is the complexity of greedy. This is expensive. So we will talk about how to speed this up, but let's see how does greedy work actually in practice. So I'm going to show you some experiments from the paper who proved this influence maximization is submodular, and did some experiments. So the setup is that they took these collaboration networks, the co-authorship in papers in archive, and our network has kind of over 10,000 nodes. We have 53,000 edges. And for example, the example of cascades would be a spread of new terminology or methods in a research area or something like that. And we are going to go with independent cascade model. And every threshold is like uniform in 0, 1. So we are going to have uniform probabilities in every edge, and we are going to try this probability for every edge, like 1 over degree of W would be the probability for edges of W. So now we try to generate 10,000 simulated parallel words to calculate the expected influence for people in this network. And the baselines are 3 like simple ones: the degree centrality as a simple baseline, the closeness centrality, which is like picking central nodes in the network, and random nodes, which is kind of the easiest baseline. So here you can see, or probably you don't see, but this best one is greedy. The worst one is we expect random, and degree and closeness are in the middle. So as you see, greedy can do much better than like random and centrality measures. And this is the case where we have uniform edge probabilities. What happens if we have edge firing probabilities, which is 1 over degree of every node? Greedy can perform even better. So it depends what is the structure of your underlying network. Greedy, like there might be a larger gap or a smaller gap between greedy and the other, like simpler strategies. So any question so far? Submodularity, probabilities, expectations, influence maximization. Yeah. Let me read. Okay, this is the active set size. This is K, target set size, and this is, I guess, the number of people. Let me see. I should look at the paper. Oh, probably the probabilities are different. This is a small probability. This is like a large probability.
Why is these graphs are so different?
Sorry?
Why these two plots are so different?
So because here, if I am activated, I am activating everybody that I know. But here, if I'm activated, I only infect a few people. Like, I can only activate a few people. So it's really more important. The initial seed is a good one. Compared to there, then even a small, like degree 1 person can infect for sure his friend, and his friend hopefully will be more influential and activate more people. Okay. No question from submodularity, from expectation, anything? Okay, such a smart class. Perfect. So, okay, now we talked about the complexity of greedy. We saw that it's slow. So how can we speed it up? So this is like we can use sketching for influence maximization problem. So how can we so first of all, like if we want to do influence maximization, as we saw, we have to produce or simulate R number of possible words. In each of them, we have to calculate every person, how many people will be influenced by a single person. We have to take an average over the number of people every person can activate. And then we have to run greedy on those expected numbers. So that's why greedy is slow. And in each of these possible words, this is the complexity of BFS that we have to run to find the number of people that every single person can activate. So this approach, sketching, is proposed to kind of reduce the complexity of OM, M is the number of edges in the network, to a constant. So we need to do some pre-processing to calculate the sketches for every node and so, but then at the end of the day, when we want to run greedy, that would be much faster. So how can we do that? So we are going to compute for every node a small sketch, or let's say signature for that node. And then we use those sketches, we use those summaries or signatures to run influence maximization, meaning greedy. We run greedy using these sketches to find the set of influential people much faster compared to the previous strategy that we saw. And this, for sure, whenever we want to speed something this much, we are going to lose a little bit of accuracy, but we gain a lot of speed up. And we are going to see what's the idea. So this is sketch that we call it a reachability sketch. So the idea is that we need this, yes?
So you said that since we are adding another kind of heuristic, so we lose on performance. So is there some lower bound on this?
Yes, I will show you, yes. There would be another epsilon, like you saw another epsilon for the expectations. Here we also have another epsilon, but these two are different. So this is strategy kind of approximating greedy. And greedy was approximating real through ground truth. So this will be an approximation to greedy. So here we also need, we take one of those possible words. When we threw the random numbers, we turned our probabilistic network to a deterministic one. So we take one of those deterministic networks and we assign a random number between 0 and 1 to every node in this network, in one of our possible words, let's say GI. And the rank of every node is the minimum number among the nodes that we can reach. Every person now has a random number. And for example, so this is the random numbers we assign to people. This node, for example, gets a 0.3 because he has the smallest rank among the people he can reach. And, sorry, it was this person. This person had a 0.4, but his neighbor had a 0.3, so he gets a 0.3. This person doesn't change, the rank doesn't change because he has the lowest. This guy would get a 0.1 because his neighbor has a smaller 0.1, and we like that. We are going to see for every person among the people he can reach. Through this now we have a deterministic network, so we can easily see how many people. And I am getting the smallest rank or number among the people I can see in a couple of steps, not only one. And the intuition is that if I'm influential, if I can reach a lot of people in this network, then my number should be small, because there is a high chance that among this a lot of people that I can influence, somebody at random has a small number. So the smaller number that I have, this means that I'm more influential. Yes?
Sorry, don't we compute rank by effectively doing BFS again?
Yes, but kind of the number of parallelized words that we have to construct here is much less than that 10,000 we needed before.
Why is that, sir? I thought we were trying to go from a world in which we have to do breadth first search over all of the nodes to one where we...
Yeah, so, okay, sorry. This is a pre-processing step. So we have to do one BFS initially, and then during greedy, there is no BFS. This is a pre-processing. That's a good question, yes. So, okay, so intuitively, if I have a smaller number, I'm more influential. Okay, so now the problem is if I do this process only once, like if I assign you, each of you, a random number, and if I try to see, if I try to get the minimum number among the people I can reach, this wouldn't be accurate, right? So intuitively, my number should be showing how influential I am. And if I do this once at random, that wouldn't be very accurate. So what we do is that we do this multiple times. So we do multiple trials, for example. So if I do this twice, so the first numbers you saw in the previous slides, and I do the same process another time, like I'm assigning everybody another random number. And again, for me as a person, my number in the second trial would be the smallest among the people I can reach. So every person has a vector of dimension, the number of trials. Let's say, I don't know, C. I guess it's C in the slides. And the good property is that it enables me to estimate the union of sketches, meaning that if I have a vector and if you have a vector, the influence of us together, union of us, would be the minimum over my vector and your vector. So we can kind of estimate the influence of sets of people using these sketches. And obviously, if I have a larger number of trials, if these vectors are larger, I get a more accurate estimate of the influence. Okay, so we saw that based on one single rank, we may not get accurate results, so we need to do that multiple times. The more we do this, we get a more accurate result, but this number kind of is orders of magnitude different than the numbers we were trying for calculating the expectations.
Are we like creating this node assignments multiple times, or we are keeping the top C, lowest C assignments? You say you are doing the trial. So basically one trial corresponds to assigning one random value to each node, and then for each node taking the minimum in its path.
Yes.
So like when we say here we are doing C trials to get C numbers, or from the same trial we are keeping the C lowest?
No, we do multiple times.
Can you explain in this example how we got 0.3, 0.4?
So I guess this, okay, let me see. So the 0.3 was there, this is this node, and the 0.5, now we should have different, okay, so this is not really like a, this is not really another example. If we change those numbers, if I'm not mistaken, we have to do that multiple times. Or probably I should check this. Probably I remember mistakenly. Okay, so now we have these sketches, and we can kind of calculate the minimum of these vectors over a set of people. So now what we can do is that we can run greedy with these sketches. So these sketches are kind of estimating those expectations that we were calculating in the previous greedy strategy. So how can we do greedy? So the way we can do greedy is that so greedy make k passes over these sketches over all the nodes in the network, and adds the person that is most influential. So who is most influential here for us? The person that has the smallest value. We consider the smallest value as the most influential person. So every time greedy goes through all the nodes and selects the one that has the smallest value in his vector. But after this person is selected, then we have to go and update these numbers for all the remaining nodes, because now this person is selected and the numbers should be updated. like if I'm selected, the influence of other people on the remaining people that are not influenced will be different. Yes.
So this assumes that all of the values for the ranks are distinct, right? That you could.
Why should they be distinct?
It seems like if they weren't distinct, like they could share, you know, they were categorical or something, that if you said, oh, I need to remove this 0.5, you wouldn't know which 0.5 it was necessarily?
I assume you have to store some more information than just a note, than just the numbers. I didn't see in the paper that we have this assumption, but I assume there are different information. Like when you do BFS, I assume it's more efficient if you kind of store which people you are influenced so that you can update here. Because whenever you calculate, you select somebody with greedy, you have to update the influence of other people. Okay, so this is now how we do greedy. And we have to update after every step. And now we can prove that, so if C is large, meaning yes.
What happens if we are updating every step? So for a particular node, the set becomes empty. Then how do we compare? Like we started with C values for each node.
Yes.
And we are updating after adding each U.
Yes.
Suppose C was 3, so it can be like for a node, all the 3 nodes have been selected. So this.
Once again.
So we have C values for
Yes.
each node.
Yes.
And these C values will correspond to some nodes in the graph.
Yes.
If those nodes are added to our inference set, then we'll remove all these C values from the node, right?
No, we don't remove, we update. Like we remove that person that is already selected, and still among the person this node can reach, we select the smallest number. So the number will only be updated. So the dimensionality will be C. Yeah. Okay, so now after I did this pre-processing, then I can find like in linear time. The expected running time would be near linear time in the number of possible words, and possible words is this C. And if this C is large enough, and large meaning we will see in the experiments like 64 or 128, not 10,000, then we are guaranteed to get this approximation with respect to greedy. So this is now an approximation to greedy, not to the ground truth. So the 1 minus 1 over E minus epsilon that greedy gives us, that is with respect to the truth, like the true influence. This expectation would be with respect to greedy. So we are trying to approximate greedy. With these sketches, we are trying to approximate those expectations, expected influences. So we are trying to, with these sketches, approximate greedy. Yes?
So will that mean, suppose that if both the epsilons are 0, then the answer we get from this approach will be like 0.63 squared of the optimal answer?
Let me think. I guess then this would be, the epsilon should be approximating greedy, not 1 minus 1 over E. That's my understanding. Because there's no submodularity here. And this 1 minus 1 over E is only for submodularity. Like we don't have like an approximate submodular for greedy. So I assume epsilon is approximation of approximating greedy. Okay. So the advantage is that we can do much faster. We can find this initial set of influential people much faster, almost in near linear time. And we have still an approximation guarantee, meaning that we are guaranteed to still perform well. And the disadvantage is that we are approximating greedy, not the ground truth. So we don't expect to do as good as greedy. Now let's see what happens experimentally. So these are the experiments from the paper. So this is like /dot network and Twitter network, and this is a /dot Twitter. This is the running time, and this is the error with respect to greedy. So we cannot calculate the optimal solution. So our best shot is greedy. And so greedy is, you can see in blue. So the error of greedy is 0 because that's the best we can do. But running time of greedy is high. So this is slow. Similarly, in the other graph, the error is 0, the running time is large. And so IRIE is like another heuristic that was there before this work, before this sketching is proposed, and you can see that in light blue. So the error is small, but the running time is kind of not very small. The same, the error is small, the running time is not very small. DEG, which is in orange, that is degree-based selection. So we select the highest degrees. So this is the running time, and the error, you see, the first node that we choose, because that is the largest degree, greedy also selects the largest degree most probably. So the error is fine. But then as soon as we keep selecting more people, then the error goes up because of the overlaps. And in the other network, as you see, like we get a really large error. So in this network Twitter, I assume high degree people are all connected to each other. For example, the example from last year was like if you consider Kim Kardashian and her sister, they are both very influential, but they influence similar people, like the same set of people. So it's not optimal to go with only high degree. And then SK, which is light and dark green, and also purple, is this sketch-based method that we just saw. The only difference is that also red. So in red, this vector of C has a dimension of 4. So it's very, very small. So we are very fast here. So we are the fastest, but we have a large error. So after that, dark green is 16. C is 16. So every sketch has a dimension of 16. So as you see, we get a smaller error, much smaller error. We are still fast, a little bit increased running time compared to 4. And then purple is 64, and light green is 256. So increasing this number, you see now you can like clearly see the difference in the running time, but the error is getting smaller and smaller when you increase the size of the sketch. Okay. So some questions that are nice in general to talk about. They're like this. Influence maximization literature is a very rich one. There are a lot of research here. Some like questions that are interesting to think about is that, so right now we didn't say about how, if we find this initial set of K influential people, how we are going to convince them to adopt the product. Like, so the first question is like, there are different marketing strategies there to maximize the likelihood of these people to adopt the product. And the other interesting question is that there is a trade-off between generality and feasibility, meaning that right now we went with this independent cascade model. If you change this slightly, you may not get submodularity anymore. So you will get a more general model, but then you can do less. You can guarantee less, and the result might be different. So what strategies, what models would work? And the last one, which is the most interesting one, is that currently we just said that, okay, we assume people will influence each other and this will spread. But what if, for example, you have two competing products? Then there will be negative influences. Like somebody is trying to promote this one, and the other hand, people are trying to promote the other one, and there would be a competition. Like these interesting questions are the ones that are there for you to answer. And with that, we are done, and thank you so much.